So
okay, yeah. So do you want to start before Unistra? So at the first for the university.
That is okay with my colleagues, of course, and that would be great.
Okay. Perfect. So I'm just going to start by presenting very briefly the digital strategy for the region Grand Est. So this strategy started with the Business as Grand Est number 2. So the Business as Grand Est launched two different main tools, the JET for the Grand Est transformation and transformation pathway. And these tools are divided into four main drivers of change: environment, Industry 5.0, digital, and health. So this change strategy is being implemented using two main tools, as I said just before, so JET and transformation pathway. In effect, the region is moving from a one-stop shop approach to a transformation pathway approach, enabling it to support companies throughout their transformation. Moreover, the JET, Grand Est Transformation, is a business community that can be able to offer advanced technological solutions to our companies in our region. And it's a resource and expertise center. So just in a more deeper way, so the JET Numérique or digital JET missions are the following ones. So there are four main missions. The first one is to structure and coordinate solution suppliers community. The second one is to contribute to the transformation of local businesses and organizations. The third one is to anticipate key skill needs and to facilitate access to the talent. And the last one, and to making a splash, so attract new solution providers and talent. More deeply, we want to promote the region, make us visible at a national, European, and international levels, for example, by building bridges with international players. So in the particular case of the JET Numérique, it's very important to include a responsible digital approach at every stage and in every solution proposed by our suppliers. So the JETs are made by several different communities, such as artificial intelligence, cybersecurity, cloud, and so on. So here today, we present this webinar under the emerging and quantum, moreover, quantum community. So it is possible, of course, to join this community using the JET website, which you can see here. So unfortunately, for the moment, it's only available in French and for the Grand Est companies. So, but if you have any question, you can send me an email. So just my last slide before jumping into quantum technology. So these quantum webinars follow on from the event taking place in our region, such as the quantum session at the 360 Grand Est, which was well attended with very high quality presentation made by Olivier Ezrati, Sébastien Bouchou from the QPerfect startup, and Christophe Couteau representing our university. So thank you for your attention for the very brief presentation, and I will now let the floor to Olivier S. from Atos. So Olivier, I will just stop sharing my screen.
Let me switch. So,
yep.
Can you see my slide?
Yes.
Okay, so I will go. Hold on. And I think I need to swap. Is it okay now?
Yeah, it's perfect.
Okay, thank you. So thank you, Mark, for this introduction. Very happy to be here today and to give you today a kind of overview of where we are regarding quantum computing. Of course, I won't deep dive into the different topics, and the colleagues will deep dive on different topics and subjects, but my introduction would be to give you the flavor of where we are with regard of technology, a kind of roadmap of maturity, and also what would be or what are the expected value and use cases quantum computing will address in the near future. So just to start, a few words on why quantum computing and what is the main objective of building a quantum computer. As you know, in a classical world, if you double the size of the problem, the complexity to solve it will be roughly the same, meaning that if you want to tackle a problem with a huge complexity, a classical computer won't be able to solve it. And the main idea behind quantum computing is to address one of the key, I would say, properties of quantum computing, and the capacity of adding more qubits on a quantum computer, and I will get back to this in a few minutes, will increase through an exponential behavior the size of the problem. Meaning that, in a few words, with a quantum computer, we could expect, as you can see on this chart, to solve very, very complex problem in a very reasonable amount of time. And on the left-hand side, you see, I would say, the classical curve and the increase of the quantum computing power with regard, again, with complexity. And on the bottom of the graph, you see what will be the capacity of a quantum computer to solve very, very complex problems. And again, as I told you, and I will get back to this in a few minutes, the main objective will be to address problems with a very complex capacity to solve it. And in particular, it can be exponential problem, it can be factorial problem, it can be computational optimization, where, again, if you double, for example, if you double the size of the problem you would have to solve, the complexity will not be twice bigger, but it could be 100 or 1,000 times bigger, meaning that the complexity to solve a problem will grow exponentially with the size of the problem to solve it. This, in a few words, means the main objective of building an ideal quantum computer. So where we are in this process, as you know, on the left-hand side, quantum computing comes from quantum mechanics, and quantum mechanics is a branch of the physics that arose, would say, beginning last century with a very famous physicist. And in 1981, 1980, Richard Feynman introduced the fact that if we could build a computer which will behave as the quantum mechanics dictate, then we could expect to have the problem, the capacity I was mentioning a few minutes ago. And this is the basics of a quantum computer is to build a quantum computer which will behave as quantum mechanics dictate, as of course macroscopic level. Say 5 to 6 years ago, IBM introduced in 2016 the first IBM network, so the first IBM computer with 5 qubits, and I will get back to this in a few minutes. Of course, 5 qubits is useless, but at least this is a kind of demonstration of the capacity to build I would say a toy model, a tiny computer working as, again, a quantum mechanical state. Atos launched an emulator, and we'll get back to this in a few minutes, 1 year later. If we go on the right-hand side, FTQC hardware, it's a kind of expectation of where we expect the maturity of quantum computer to be able to solve, I would say, real problem. And as you can see, we expect 10 to 15 years from now. Why? It's due to the fact that today it's very complicated to build ideal qubits, and I will get back to this in a few minutes. And as you can see, to have a FTQC, what we're calling a fault-tolerant quantum computer, we will need to add logical qubits. We need to be able to introduce error correction to be able to build FTQC. As you can see, we are not there yet today. However, in, I would say, midterm, let's say in 5 to 6 and 10 now, what you could expect is to demonstrate the quantum advantage. The quantum advantage being the capacity to solve a real problem on a quantum computer and demonstrating that this problem will be faster than any classical computer. Again, we are not there yet, and we expect to be able to demonstrate the quantum advantage for some very specific application and introduce to solve it, and I will deep dive again there, what we're calling error mitigation, the capacity to, I would say, mitigate the error at the hardware level, as we today don't know how to build, again, logical qubit, and in particular, we're not able to introduce error correction at the hardware level. So, and then today, we are in the phase called NISC era, noisy intermediate scale computing, meaning that we can build quantum computers. However, all of them are noisy, meaning the qubits are noisy. They are not ideal, meaning that, of course, we will not be able to get benefit of a quantum computer today. And as you can see also, and I will get back to this in a few minutes, Atos and are evident address a different way, meaning that the one key problem is to develop application. This is why we introduced in 2016 a quantum emulator. Again, this is a kind of global flavor of the roadmap and when we expect to have, first of all, a quantum advantage 5 to 10 years from now, and when we could expect to have, with the ideal quantum computer 15 to 15 years, 15 to 20 years at this view. The first, I would say, the first step for building a quantum computer is to build a qubit, okay? Again, I won't deep dive here in a different technology, but just keep in mind that there are today 6, 7, I would say, technology that will let you design, build a qubit. It can be, as you can see, ion traps. It can be a super communicating way. You can use photons, okay, to exhibit this quantum effect. In some cases, you could also use a silicon spin qubit, exactly what CEA is doing Renault, for example. You can use cold atoms. As you can see, 5 to 6 technology that will let you in different, I would say, modes to build a qubit, and this qubit will release the capacity to behave again as the quantum mechanics dictates, and in particular to exhibit the two effects well known in quantum mechanics, known superposition and entanglement. And again, a qubit need, of course, to be able to have these two properties to give the capacity I was mentioning a few minutes ago. And as you can see again, many actors addressing different technology with different maturity, different, of course, each technology is not ideal. I mean, there is no one technology which is much better than the other. Every technology can be good or bad, depending how to use it. And of course, depending, and I will get back to this in a few minutes, the scalability, which is a key point. I will just show you one slide just after. Just so keep in mind, the first step is to design a qubit. Now, however, on top of this, keep in mind also, and again, I won't deep dive there too much, but keep in mind that there are today 3 main, I would say, flavor to program a quantum computer. On the right-hand side, it can be quantum gates, and I will show you some example in a few minutes. Quantum gates meaning that you will be able to address each qubit and to program, to design a circuit, an algorithm, through applying to each qubit gate, and you see the small, I would say, rectangle on the right-hand side, XH gates will apply to qubits a signal, and this is how you will design a circuit. This is, in theory, the more, I would say, general purpose quantum computer that will let you address every kind of problem. On the right-hand side, on the left-hand side, you have quantum annealers, and in particular, D-Waves is very well known on this. It's a different way of using a quantum computer, and there you will exhibit on top of the 2 effects I was mentioning, what we're calling a quantum effect, a tuning leveling effect. The main objective in this way of programming a quantum computer will be to have kind of problem, and you will let the problem evolve to find the minimum of the problem. And in particular, for optimization, you have you have, for example, a very complex problem designed by the Hamiltonian, and the question is, you will let evolve this Hamiltonian to find the minimum of a function. And in particular, in quantum chemistry, in some problem, in some logistic problem, this way of programming a quantum computer would be very helpful. And in the middle, you have the quantum simulator. In France, Pascal is leading this activity, Pascal in Paris. It's a kind of way of quantum annealers where you can, I would say, weight the different qubits through a different, I would say, model. And this is a kind of way of using annealing problem for a kind of more general way of programming a quantum computer. So keeping in mind, just as a recap, the first building block is to design a qubit, and then to choose, I would say, what will be the way you will design your quantum computer through the three models I was just mentioning. So I was mentioning that we are in the NISQ era, and the good news today that there exist many vendors providing some quantum computers with different maturity. I put there some picture. Of course, many logos are missing, but you can see in the middle D-Wave, which is exactly annealing. On the left-hand side, the IBM one, which is supercomputing. You can see somewhere Pascal on the bottom left, which is neutral atoms. You can see Pascal, Candela on the Candela is photonic approach, and of course also, I mean, in Grenoble, a sequence now probably is pushing a different technology through spin qubit. And also, I mean, I was mentioning, I mean, we are in the process of working with the Grand Est region, and in particular, working with QPerfect and QAccess, which are also leading quantum computing activities for East France. So keep in mind, many solutions exist. However, all the solutions I'm showing there, again, are NISQ, meaning that it can have from 5 to, let's say, 500 qubits. However, all of them are noisy, meaning that, again, you will not be able to get benefit from advantage through a performance through the NISQ era due, again, to this noisy environment that won't let you gain advantage of a quantum computer. And one problem I would like to mention is the scalability. I mean, building one qubit is pretty easy. The main problem, if you want to build a quantum computer, is to add many qubits. And as you can see on the left-hand side, if you want to interconnect two qubits, that's easy. Just to draw a line between the two qubits, and you have a two-qubit system. Building a three-qubit system is still easy. I mean, you have a kind of triangle, and each qubit will be interconnected. However, the problem is very complicated if you increase the number of qubits. And I just depicted there some picture. And as you can see, if you add many qubits, the complexity to interconnect all the qubits is exponential complicated. And in particular, in the rectangle, I'm just showing the graph for a 16 all-to-all topology, meaning that in this graph, each qubit will be interconnected to the whole neighbor. And as you can see, this model will not scale. It's not. You can't expect it to be able to grow the number of qubits and to have a all-to-all topology. This is why, I mean, when growing the number of qubits, you need to choose a given topology. Meaning, I just show you on the 65 qubit system, the Numérique system. This is a 65 qubit system, and as you can see, IBM decided not to interconnect all of them, meaning that it's a choice to say, okay, what will be the ideal connectivity to let you interconnect a certain number of qubits to add more qubits and to be able not to design the capacity of of building the coherence time, and the time between all the qubits will be coherent, meaning that behaving as, again, a quantum computing state. And as you can see, this is a key challenge today. And as you can see, today, the IBM is leading the race, I would say, on the supercomputing track with around 500 qubits, 433. But as you can see on the left-hand side, we expect that to have a kind of FTQC computer, to have this advantage I was mentioning, we would need at least 1 million qubits. So we are very, very far from that today. This is why one of the key challenges, and I will get back to this, is on top of developing hardware, one key topic is to develop application and use case for taking advantage of quantum computers. And again, 1 million qubit is a kind of, I would say, a rough estimate of how many qubits would be needed to be able to design a FTQC computer. And again, this is why I was mentioning 15 years from now, it's a kind of rough estimate of the maturity of the technology. Now, I'll just say a few words on technology, just a few words now on programming and application. This is something to keep in mind. There are no portability between classical and quantum computing, meaning that to take advantage of a quantum computer, and this is true for all the technology and all the programming model I was mentioning, you will need to redesign from scratch the algorithm you will need to use. And in particular, if you have a problem today running on C, C++, Fortran, Java, I don't know, on your classical computer, to take benefit of a quantum computer would need to redesign from scratch your algorithm. And I just show you there one example of what we're calling a quantum circuit on a quantum gate based model. On the left-hand side, you have Q0, Q1, Q2 are the qubits, so it's a 3-qubit system. And to design my algorithm, as you can see, I will apply to each qubit gates, H, X, V gates. And this is how I will design and start developing an algorithm. And as you can see, it's very, very, very different from what you can do. Again, it's not C, it's not C++, it's not Fortran. The way of programming a quantum computer is very different from what you know in general. And of course, on top of this very basic layer, you could use some Python libraries to manipulate the qubit. This is the blue rectangle I was just showing. It's exactly the left-hand side through a Python programming model, just to let you some easy way to manipulate the qubits. But as you can see, that's not be trivial to do that. And on the bottom of the slide, I just draw an example of what is a 5 QFT, a quantum Fourier transform on a quantum computer. This is exactly how it works. And as you can see, it's very different from what you could know on a classical way. So just keep in mind that programming a quantum computer is not an easy task, and it's a real different, I would say, paradigm from what we know on a classical world. Now, moving from programming to use case. And this is, of course, the main advantage and what we're targeting is building a quantum computer. The main objective is to solve problems that a classical computer won't be able to solve. As you can see, and this is what I was mentioning, there are no, I would say, application portability from classical to computing world. So meaning that you will need to redesign, to redraw all the algorithm known on a classical mode to a quantum computer. And the first step is to identify what would be, I would say, the algorithm that will take benefit of a quantum computing speedup. And in particular, all the problems in a classical way are not, I would say, will not be able to address this boost from quantum computing. I will just show you a few problems. One key challenge today is to identify in different industry what are the problems which will behaviors as being capable of being accelerated by a quantum computer. And as you can see, I mean, some problem, classical way, will stay on the classical problem. Some problem could be addressed by a quantum computer. And of course, some problem would be accelerated through FTQC computer, and there where I mean, a classical computer would not be able to tackle this problem. And one problem, I don't know if I have one slide on this, is of course, just keep in mind that a quantum computer will never be a standalone computer, and we will always need a classical way to work. This is what we're calling hybridization between classical and compute. If we go one step further, we are in the process, as I was mentioning, to identify what are the main industries, domain, where we could expect some problem to be accelerated by quantum computers. And the good news, there are many problems like this. In this slide, I just recap through 4 families. Quantum simulation, I mean, if you want to do physics, quantum chemistry, material design, of course, we could expect a boost from using a quantum computer. Some problems where at the end, you will solve a very complex linear system, and I show you some example in finance, in telco, in machine learning. This problem will be accelerated again by a quantum computer. Quantum works, many problem optimization. I mean, remember, I was mentioning this D-wave model when adding problem. If you have a problem and you want to find the minimum of a very complex problem, quantum works will be something that for sure will be addressable by a quantum computer. And a new the topic which has been arising is quantum machine learning, QML. It's using machine learning for addressing quantum computing. So keep in mind, so many domains, and I will just show you something very with more detail where we could expect some advantage of using a quantum computer. Just this is kind of summary of the impact, and I know that Charles will deep dive on some topics. Keep in mind that in research, chemistry, fluid dynamics, batteries, CFD, all the problem behind will take benefit of a quantum computer. Of course, there are also many operations which are not research, but financial operation, logistic, transportation, marketing, where you have very complex problem. And this problem and the algorithm behind the problem will be eligible, I would say, to quantum computer. And as you can see, many industries will be able to tackle and to address the benefit of a quantum computer in mid or long-term environment. And of course, there is also a key topic, and I will deep dive there. It's defense. I mean, as you may imagine, there are many topics in the defense era where quantum computing will also bring a real benefit. So just a kind of summary. The domain are pretty large, pretty broad, and many topics, depending on the algorithm, will take benefit of a quantum computer. Just a few words on what Evident, former Atos, is doing on this. I mean, as I was mentioning, mostly hardware starting this presentation. We as Evident, we are not working on qubits. We are not designing qubits as I was mentioning a few minutes ago. Our main objective is to design a kind of building blocks, which is an emulator of quantum computing, which will let you develop your algorithm, whatever the technology or the programming model I was just mentioning. And the main objective is to have this environment that will let you develop your algorithm agnostic to the different technology I was mentioning before. And this technology was known as QLM, quantum learning machine. And a few weeks ago, we announced kind of a new strategy called now Captiva. And I will say a few words on Captiva. So keep in mind that we are pushing an agnostic view to develop algorithms for quantum computer. And one topic which is also key in the evidence strategy is the hybridization between HPC and FTQC or LSQ, same wording. The evidence is very active in HPC. And of course, as we know, we see quantum computing as an accelerator of a classical computer. And this is where hybridization takes important, and we are deeply involved in developing different programming models and different APIs to interconnect, I would say, classical computer and quantum computer. So just in a nutshell, the overall Captiva strategy. On the right-hand side again, but I won't deep dive, the hardware line and this emulator line with different solutions. And again, it's not the topic today. And on the left-hand side, I think this is key, is the capacity to bring expertise to our customers and partners. As you could see, identifying a use case is not easy. Programming a quantum computer is not easy. And what we did and what we're doing at Eviden is to bring expertise to our partners through training, through consulting, through support, to help them, first of all, identify use cases and then start developing their use case on the different technology I was mentioning a few minutes ago. So just one word on the Captiva environment. And again, I won't deep dive there, but on the very bottom, you have all the programming environment. Okay, but what is very interesting in the Captiva environment is the three orange boxes will address the different programming models. Just keep in mind that a few minutes ago, I was mentioning the three main programming models, quantum gates, annealing, and analog. This is exactly what we are doing in the Captiva world. We are pushing different, I would say, building blocks that will let you design your algorithm, to develop your algorithm on these three, I would say, programming environment through different tools, and I won't deep dive on that. But the main advantage that you have no reason, I would say, to choose a given environment. You develop agnostic on the QLM, Captiva, and then through connectors, you will be able to address different technology, different out technology, and this is a kind of interface through an emulation on Captiva and accessing real hardware through what we're calling interface, and this is a way, again, it will let you design on Captiva and then access real hardware. And just to present the global environment we are developing, we have a broad ecosystem working with us. On the right-hand side, as you can see, mostly hardware vendors in France, IQM, which is Finland, but Pascal, Cordella, Alice above, we are working with them, meaning that we include their technology in Captiva, meaning that, again, you will be able to develop your algorithm on Captiva and then address all this technology through connectors, let you access all this technology on a, we say, transparent way. And in the Captiva, you will find all the building blocks that will let you address all these different technology in terms of qubits. And on the left side, we are also building a very large ecosystem with software partners. You see some names. Many of them are, I would say, addressing a particular environment. For example, in Confi, as you can imagine, they are specialized in finance, and Confi is working, by the way, most with Strasbourg, and that in the process of designing algorithm for the finance space. Colibri TD, for example, they are mostly working on CFD and solving EDPs, partial equation differential in different environments, and particularly CFD, and we are working with them on different projects, in particular for combustion. And it is key to have this global environment working with us on the hardware side again, and on the software side, bringing expertise on the industry where we're not experts. And last slide, I think, yes, last slide is the global ecosystem. As you can see, we have more than 30 customers, partners working with us. Of course, academics, but the good news, and we see many, would say, private customers, I mean, industrial, BMW, EDF, and again, when this customers are in the process of identifying a use case, saying what at EDF or BMW, what are the 2, 3, 5 use cases that will take benefit of a quantum computer, and what will be the effort to develop this algorithm for a quantum computer. So it's a growing environment, and this is, I mean, something which is very interesting to see that now with the 10 years now, mostly quantum computer was supported by academic partners. And what the good news is, we see many now private customers, industrial, coming in this space and starting developing their new algorithms. I think I will stop there. I will be there. I mean, for all the seminars. So if you have some questions at the end, I will be happy to address them. And thank you for your attention.
Thank you, Olivier, for this presentation. I don't know if you have already a first question. I don't have any question in the chat, but if you have one, you can just raise your hand or open your mic. Okay, I think we are going to take the question at the end of the presentation. So, Charles, if you want to go, the floor is yours.
Thank you so much for inviting me to that webinar in English. So the first question you could have is an IT services company or a digital services company such as Soprasteria, or what would be, we are not a quantum computer maker, we are not a quantum software editor. What could be the role of an IT services company, and somewhere in a nutshell that will be what I will try to explain you today. So before getting to the heart of the matter, in preamble, a few words about my company. So Soprasteria is a leading European tech company within 2022, plus 50,000 employees. A turnover exceeding 5.1 billion euro. We are in the top 5 of the European player, and we operate in about 30 countries. But last but not least, if all the digital services companies are alike from afar, they are ultimately very different closely, and that's very good. And what makes Soprasteria different is our ambition to support the business transformation of our customers, for which technologies are major levers, compulsorily major levers, but not a goal in itself. So we therefore approach technologies as well as quantum from a business standpoint, from the usages, with the objective of getting tangible benefit. And so, taking into account the brilliant presentation just done by Olivier, may quantum investment be a paradox, because the digital quantum computer, noisy, capable of providing thousands of qubits and chaining thousands of doors, is expected at best in 10 years, but some speak of 20 years. Why, nonetheless, are we investing? So first, it can come much faster than expected. Remember the Apollo program, so let's not underestimate the talent of human beings. And second, there are critical usages for which our customers can't afford to be left behind. So the Soprasteria commitment is one, to not oversell, is twofold. One, to not oversell the quantum technology, and two, advise our clients to prioritize the use cases that make sense. And here, the heart of why Soprasteria is investing in quantum, because this is just necessary to the quantum ecosystem on three major subjects. A, we have to translate the technological promise into business increment. B, we have to bridge the gap between the business problem and the mathematical expression, and how to tackle them with algorithm. And C, well explained by Olivier just before, quantum computing will need to be integrated with traditional computing. So this is why it's so important that as part of the ecosystem, digital IT services company foster the quantum development. And regarding the use case, no surprise, you can have typically a subject about cybersecurity, about optimization, about simulation. And here, what is really important is to well select the subject. And our first recommendation is to focus on ones for which our clients cannot afford to be 3 years late, either in terms of competitiveness or in terms of sovereign issue. So typically, we have the quantum cryptography with the use of the physical layer of networks, of post-quantum cryptography consisting of augmenting existing setup with new ones in order to protect against future decoding, leveraging the quantum computer. Simulation, so topic, a lot of R&D department will be very interesting by leveraging the quantum. And finally, optimization topics that concern all the sector without exception on operational research or artificial intelligence topic. And here, in a nutshell, this is how we address the problem in a four-stage approach. The first one is, I insist, will be to identify and to prioritize the good use case. Once it has been decided and selected, it must be first expressed mathematically. So we then try to use or develop an algorithm providing the best solution, something that we are doing for years. But very often the volume of data makes it ineffective. The complexity is too important for a classical approach. So typically the answer is available too late. So this leads us to develop a new algorithm, which by means of heuristics makes it possible to obtain a result certainly less precise, but in the time expected. And then comes the stage of developing a quantum algorithm sometimes several, which consist first of all in proving the concept that the problem is solvable in a quantum approach. And in this case, we use a emulator to compare the result with a traditional algorithm. And that step, if it is successful, is the first tangible and concrete result. It is a proof that the day when a digital quantum computer is available with the necessary power, our customer will be ready. And last but not least, we can then continue and work to investigate, as suggested by Olivier, intermediate technical solutions such as quantum-inspired analog computers like D-Wave or Pascal, or NSIQ solutions such as IBM or Candela. One point also which is really important and related to the ecosystem I talked about a few slides before, it is important to be able to test the different technical options available. And Sopra Steria has a powerful ecosystem of strategic partners such as AWS, Google, Microsoft, IBM, and OVH Cloud, as well as startups. So Sopra Steria invested in the first investment fund dedicated to quantumation, making us de facto indirect shareholders of some 20 of the world's most promising startups. And in a few months, we have already several projects that have passed the proof of concept stage, just explained two slides before, and are by now evaluated on the available technology. So even if it is confidential, I can anonymize two examples. So the first one is to find the best configuration of a graph in the world of the telecom. And the second is the optimization of the allocation of scarce resources in space. So the teams are currently testing the different technologies available, allowing us to anticipate which one will be able to give our customers the quantum advantage over these users. The digital services companies, such as Sopra Steria, will have a very, very important role in scaling Numérique. And my conclusion is quantum is finally and now with reasonable goals and tangible and concrete results. And if you have any question, I would be very happy to answer them.
So thank you, Charles. So as I said for Olivier, for the moment, I don't have any question on the chat. So I don't know if anyone have a question. You can just raise your hand or open your mic and ask a question, or you can also.
I stay connected anyway.
Yeah. We can also take it at the end. So if we don't have question for the moment, we're going to move on the university part. So with Christophe Couteau from UDT. Okay, so Christophe, the floor is yours, so you can share your screen if you want.
Yes, let me find, here we go. Alors, voilà. All right. So we even have 5 minutes, 5 minutes early. That's good. Non, attends, il faut que je have to share. So I can share just that. Is that right now?
Yes, perfect. We can
Yes,
share the screen.
and you can see my mouse as well if I need to move about. Okay, perfect. Yeah, so good morning, everyone. So yeah, my name is Christophe Couteau. I'm a professor at the University of Technology of Troyes. And I'm going to talk about quantum technologies at the UTT and mostly two sides, two aspects of it that we are tackling or trying to tackle at the UTT. And also, I'm a director of one of the 5 research units, the Laboratory Light Nanomaterials and Nanotechnologies, or L2N, which is a joint UTT CNRS research unit. Yeah, so well, just to present the university, so it's in the Champagne region, and we have 5 research units. And as I said, so the L2N is the one I'm involved in, but I will show also some work from the LISTEN research unit that is linked to quantum technologies. Otherwise, for the L2N, so it's mostly an experimental physics laboratory with a bit more than 1,000 square meters of lab space and 3/4 of it in clean room. We also have a graduate school called NanoFOT, which is a master to PhD level. And just aside, I mean, it's not the subject today, but in the region, there's a lot of stained glass, and there are links with nanotechnologies, which, and we also have projects within this theme, which is more multidisciplinary. So in a nutshell, the laboratory is about 100 people. We have 23 ECs, enseignants-chercheurs, so faculties, 3 CNRS researchers, admin staff, engineers for the platform. PDF is postdoc fellows and PhD students, visitors, interns, and so on and so forth. We have various contracts in terms of research contracts with public agencies, but also the European Union, but also industry or the region. And what we do, amongst many things, but we do publish articles, so it's about 40 to 50 articles a year. And we have indicators such as impact factors, and that so for us is 4.5, whatever it speaks to you or not, it's not bad. We go into conferences and we patent some of our technologies. And in a nutshell, what we do is we try to work from fundamental issues to applications, and I gave 2 different examples. So one of them that is directly related to the subject of today, because it's something I work on. What you see here is a spectroscopy, optical spectroscopy signature of a particular defect in a diamond matrix at low temperature, at 4 Kelvin, so it's minus 270 something degrees. And what you can see here is these 4 lines. It might not speak to you, but what they are is they're actually sort of atomic-like transitions. So it basically shows that this is almost behaving like a single atom in a matrix. And this is good because this object can be used as a qubit, specific qubit, to produce photons that can then be used also as quantum bit, and I'll come back to that later. And some other aspects that we deal with at the L2N, which are not necessarily quantum related, is applications. So here's an example of an integrated sensor called the surface plasmons resonance sensor. Whatever, it's basically a biological sensor. And there's a startup company called PhasLab Instrument that came out of this. That now produces this technology that came out from the lab. And so again, one more slide on the lab in general, and I will focus more on the subject of today. So what we do is we observe, study, and control light at a nanoscale. And we have 4 research topics. So one is called interactions, light matter interactions at the nanoscale. One is about photonics for devices, and what I'm going to show you today is more targeted on this topic, is to use photons as qubits, as quantum information carriers. And I also showed you what kind of object can do that. We also have some topics in nanobiophotoниcs and nanosensors for biology. I already gave an example. And we are nanolab, so we do a lot of fabrication and nanosynthesis in our clean room. And with this, we have our 2 pillars. So one of them is our technological platform called NanoMat, which is known from the CNRS network. And we also have, as I said briefly, a specific graduate school on nano-optics and nanophotonics, where again, it's not just about quantum technologies, but this quantum technology through nanotechnologies are dealt with in this school as well. Right. So if we dive into the subject, well, I think by now my colleagues have been doing an excellent job as defining a qubit. So I won't have to define it again. Simply just to set it for what kind of qubit we want. So basically, at the end of the day, we want something that gives us two states, which can be in a superposition state. And there are many physical systems, it has been mentioned already. And this is sort of a mathematical view, but behind it can be any physical system. So in a particular case, as we will see, we are interested in photons and using light as our qubit. So the question is, how do we define the 0 and 1 on a single quanta of light? So light is made of particles called photons. So how do we code quantum information onto these objects to have such a superposition state? And again, very different from has been mentioned already, from the different from the classical transistor, which is one or the other state, but not two at the same time. So this is a classical transistor, but we want a quantum transistor. And for that, we need these two states to be in a superposition. So for that, we use light. So we use photons. So if we take a step back, so I didn't put some slides on this, but I can show them after. I thought it would be a bit too much, but light is encompassed into what's called electromagnetism. So this has been known for a couple of centuries. And this is a classical wave physics phenomena, no problem with that. And light is very well understood through what's called the Maxwell's equations. So there are 4 of them, which deal with the electric field, magnetic field, and the electromagnetic field. And there's no problem with that. And one particular property of light is that light can be polarized, right? So you have here an example of what we call vertical polarization. Well, actually, you have 2 examples of vertical, 4 examples of vertical polarization. So of linear polarization, sorry. So you can have vertical polarization, so light would oscillate vertically. You can have horizontal polarization, so that means light can oscillate horizontally. And you also have diagonal and anti-diagonal. Okay, so all of those are linear polarization because the oscillation, so the light goes towards you while oscillating, but the oscillation is along one axis, so like this, like this, like this, or like this, all right? And it can be any others, but usually we use these 4 because they are related to the axis of propagation of light. I mean, this is known, the polarization effects. We can have that. We can have polarizers on cameras, on glasses, and so on. No problem. You can have a bit more complex polarization where you can have circular polarization. So that means when the light goes towards you, it can go circular right or circular left. So I'm not sure that you can actually see me moving right now because there seem to be some lag, but never mind. And yeah, so this is all known, no problem. We understand that Maxwell's equation gives us that. And the thing is that actually what we can do and what we can show is that these equations and therefore all these properties also work at the single photon level. Okay, so it's been known that light is not just a wave effect, but is also something that is made of particles called photons. Okay, and that is typically the known quantum mechanical sort of paradox of an object being a wave and a particle at the same time, where photon is definitely bang into this property where a photon is a wave, is a particle. You can record it. You can see a spot recording it on a detector, but is also a wave and therefore can behave the same way and can be polarized. And that's good news for us because then we can use polarization. This is one way, there are others, but today I'm going to concentrate on polarization to encode quantum information onto the polarization state of a photon, because a photon, on the other hand, is a quantum object that is obtained when we so-called quantize Maxwell's equation, okay, when we take it to the quantum regime. And it's very good because, well, I can say, okay, well, if I have vertical polarization, I call this my zero state. And if I have horizontal polarization, I call it my one state. And the good thing is that we can see straightforwardly that I can get a superposition state of 0 and 1 with a diagonal state, because a diagonal state is a vector that can be projected, that has two projections along the horizontal axis and along the vertical axis. So if I want to represent that mathematically, classically or quantum mechanically, this is a superposition of the two cases. Okay? And the secular left and secular right, it's the same thing, except that now there is a complex number. There's a phase between the two. They are actually related. They're not disconnected, but same idea. So here we go. So in other words, photons can be used as a qubit, as a quantum bit. Here we code on the polarization, but as I said, there are other ways of encoding the quantum information onto photons, but this one is pretty visual and can speak to people. And the good news is that because light, so is an electromagnetic wave and also particles, as I said, but the good news is that standard optical components that we use for day-to-day light, I mean, right now I should probably be needing an optical density to attenuate the light coming from the sun behind me. But I can also use what we call half-wave plates, or quarter-wave plates, or polarization beam splitter, or even intensity beam splitter. So all these components work with standard light, with a laser, with a flashlight, with anything. But because the equations, the Maxwell's equation, whether they work for classical light or quantum light, the properties remain the same. So it means, in other words, that I can manipulate photons, so therefore qubits, with these very same optical elements. I do not need specific equipment for that. I can use these elements. And for instance, what a half-wave plate does, it's something that can rotate a linear polarization into another one. So you can see that with this simple element, you can come horizontally and you can be a diagonal polarization after it. So this got a name in quantum information. This is called an Hadamard gate, or superpositioning gate. So here we go. This simple element will be my quantum gate, a single quantum gate, a qubit gate for my photon. And then quarter wave plate will make a circular polarization. So it's also an Hadamard gate, but with a phase. A beam splitter, a polarization beam splitter will separate two states of polarization. So it's a way of splitting the property of a qubit, or to split different qubits, and so on and so forth. Okay. And so here we go. So what we do is we go in the lab and we use, different components. So you can see an example here. So this is a typical optical setup. So it's a bit of a mess, but this is how it goes. Where you have some mess. Why? Because you have different components. So you have these polarization components. You have mirrors, lenses, and optical fibers, and so on and so forth. Because you need to create these photons, you need to manipulate these qubit photons, as I just showed, and then you need to detect them. Okay. But in other words, these optical setup are basically the equivalent of quantum gates that you can use. Okay, and so that's what we do. And for that, you need what we specifically focus on. We focus on the source of single photons of these qubits. So I need to check the time. Yeah, I think I'm fine. I'm a bit there. And what we do is we use, as I already mentioned, this defect we call color centers in diamond. So here's a diamond matrix, which is made of carbon, and you have these different matrix defects made of germanium, silicon, or nitrogen, and so on. But the bottom line is that they can be into a nano form, and therefore can be used as a local source of photon qubits. Okay, and here's the optical spectrum. Doesn't necessarily speak to you, but it's to give you the different spectrum of these three different centers, and you can see they are different. So therefore, each of them will have their different properties and pros and cons. But the bottom line is that this is a very good source of qubits. Okay. Right. So this is the part on the sort of hardware part that we work on at the UTT. So the at the L2N, so the what is called the quantum photonics approach to build these photon qubits, to manipulate them, and so on and so forth. Of course, as you may have guessed by now, it's always a bit more complex than what I just showed here, because there are many properties you have to take care of. And that's why it's a specific system. This is something that we're working on at the UTT on one aspect. So the second aspect I want to talk about quickly also, not just because the time is running, but also because I am not really an expert in that, is done by my colleagues at the computing lab, computer science lab called LISTEN. And these colleagues are specialized in what's called operational research. And this is known in computer engineering, computer science. It's optimizing supply chain issues. Okay, and the idea is, what they started to do is, well, can we try to find a quantum optimization, along the same lines as was shown before? And so if we take a step back, so what is operational research? So that so far so good, one can understand. So you have some objectives, which can be to maximize benefits, minimize cost, satisfies the end clients. You have some constraints, which is material issues, human resources, transportation, storage zone, availability, security environment, market uncertainties, demands, raw materials, and so on. So you got all of this, and you have a chain. So going from the supplier or supplier, you have a company that would make the stuff, whatever stuff that is, and you have the client or the client's client. Okay, and so that means you have a physical flux and a data information flux. And the idea is to optimize these both physical and to optimize the physical thanks to the data information flux. Okay, so this is in a nutshell operational research. And the idea is, how do we use quantum to perhaps go further than that? Well, just briefly on how do they do, I don't, but how do we do in operational research? There's some mathematics and computation. Is you take a problem, you try to model it, you have a method to model it, and you get a solution to it that is satisfying your needs. Okay, in a very quick chain, this is how you usually do. And so the idea is to say, well, can we apply quantum computation to these kind of problems that they have in operational research, like scheduling, sequential ordering problems, and so on. And one of them that can be used, so that's what my colleagues are working on, is to see, say, the Grover algorithm, the quantum Grover algorithm, and to try to see if we can get exact optimization, exact within the error bar, of course, of a classical problem using sort of classical Grover quantum algorithm. Okay, so that's one aspect. And the reason being for that is, as has been said, we do not have a real quantum computer, or not a full one yet. So already to see whether this can bring some benefits. And what my colleagues have done is they've tried also, I believe, like Charles was mentioning, to take a given problem and to play around with, so in this case, with D-wave solver, and so here's the chain. So this doesn't speak to me really much, but it might speak to people who are in this field of modeling with Docplex, and then there's a method that you want to translate to what's called QUBO, and then to the icing problems, and then you want to use the quantum solvers. That I already mentioned before, that D-wave can so that's where you enter the D-wave. So that's where my colleagues try to compute this problem and test it on D-wave and see what comes out. So typically, this is the kind of ideas and kind of problems that my colleagues I try to look into, and perhaps to find problems that can be solved more quickly using sort of quantum computation algorithm. And to finish, I've got some online courses that are fully available on YouTube, because I've been doing this. So if you want to know a little bit more on the topic, then you can go on YouTube. You type QX01 in my name, and you should be able to find them. And I think this is it. Thank you very much. And if you have any questions, then I'd be quite happy to take them.
So thank you, Christophe. So as you will leave us within 10 minutes, something like that, if you have questions from Christophe, you have to ask it now, because so we can also write him an email if you have question later.
Yeah, it's down here. Oh, well, it was down here, but yeah.
Perfect. So for the moment, I don't have any question on the chat. So thank you, Christophe. If you have
Thanks to
questions
my colleague to swap it. So yeah, thank you.
Perfect, thank you. So next one, Frederic, for your class, so Reims.
Yes, thank you, Mark. So I share my screen.
Yes.
Okay, can you see it now?
Yes, we can see it.
Okay, good. So I want to first of all thank Grantino's team for bringing this opportunity to present our activities. So my presentation will be very short. Maybe I can put it in full screen. Is it better like that?
Yes.
Yeah. Okay. So I will be very short, and I won't be very technical at all. So I want to present you mainly a project we are a partner of, which is called the Competence Center, which is a European project, which aim at bringing together industrial and academics to work on project and to support the private companies to help them working on their projects. But before that, I want to present to say a few words about our computer center, which is called Romeo. And our ecosystem, how we are working, and what we do at the computer center. So I don't know if you see my mouse. Okay. So our main mission is, of course, to support the research of our researcher at the university. So that's mainly in the domain of chemistry and physics, mathematics. So that our historical mission at the university. But more and more, we are opening to the private sector and the private companies to help them tackle some challenges and to bring them some compute resources in different aspects. It can be on the artificial intelligence domain, HPC domain, high performance computing domain. And also we have some actions about quantum computing. And this is through mainly some projects, European projects, and I will talk about that a bit more later. Another mission we have is a mission to teach our students how to use such kind of supercomputer. So we're developing tools to interact with mainly developing tools for teaching, helping our teachers to present materials that the students can use on the real supercomputer. And also we have strong interactions with institutions like CEA and also laboratories from the university. And that brings us to a domain which is a kind of research and innovation domain, where we're exploring some subject about testing new materials, testing new ways to do things. And also we have a strong history about using new materials, and especially we were at the very beginning of the the adventure of GPUs, and we are also the one of the only university in France to have a quantum learning machine that Olivier told about at the very beginning of this webinar. So yeah, just a few words about how we are working with companies. So mainly we have two modes of collaborations with companies. One mode is a mode more on we say more relaxed mode, where we're entering a dialogue with companies and help starting a collaboration on small projects. And these small projects can give birth of internships, maybe also thesis, and maybe why not writing of projects like ANR projects. And the second mode is more a mode, a services mode, where we can bring expertise, can work on proof of concept, and of course we can give access to our compute resources, giving support to how we use the supercomputer, helping people to start launching jobs and using at the best of their capabilities this kind of materials. We can give also some training on how to optimize code and to use kind of materials like GPUs, for example. And of course, we are also providing compute resources on a by usage basis. So now I want to talk about this European project, which is called the Euro Competence Center project, which is a part of the European High Performance Computing Joint Undertaking project. So we're on the phase 2 of this project. So there was a Euro CC1 before the Euro CC2, which is the project at the state it is now. So basically, this project is a network of 33 national competence centers, which are organized around performance computing in general, not just on quantum computing, but it has the aim of bringing together in industrial and academics on subjects around HPC, artificial intelligence, and high performance data analytics technologies. So the missions of the competence centers will be to be like a hub where companies can find an academic partner to work on different subjects and on different problematics they have in their business. In the competence centers, they will find some services and some support offer, some help for the use of high performance resources, and also some training on different subjects. It can be on high performance computing, artificial intelligence, of course, and quantum computing. And also there is some events which are organized and some job offers that can be advertised. So the competence center relies on a network which is called Mesonet, which is the gathering of the computer center in France, which are intermediate size, which is why we call them Mesonet. So that's several centers all around France, which are specialized in certain subjects. And here in Romeo, we are specialized in training on the HPC and also on quantum computing. because I will tell you a bit later, but we are lucky to have a quantum learning machine from Evident, so that make possible to have to experiment with quantum computing. So within the competence, the real Euro Competence Center, we have a tailor-made support. So when a company wants to work on a subject, so there is a special path they can follow within the competence center, and we provide a free support, which consists of an analysis of what's the problematic, and to settle on the different questions we will work on, and we will have a proposal of what the competence center will provide to the company, how we will work together, and we will elaborate on a plan to what we'll do later. So there is a contracting phase, and then we can go further to work and tackle in more depth the problematic of the company. So depending on the project, of course, it can take sometimes from a couple of months to several years. Here is a sketch of the training we're offering, we're structuring actually about quantum computing. So that will not be the definitive offer we'll have, but it's essentially it will resemble what I show you now. So basically, we'll have a session, an introduction session, where we'll present some basics about quantum computing, which is scheduled to be 1 day. And then we'll have some advanced sessions up to 3 days on different subjects, and presenting mainly the programming environment, what is quantum circuits, and discovering some basic algorithms. And then there are more specialized, like here on the right, more specialized sessions on different algorithms, which are of different interest depending on what we're interested in. And also some sessions about applications, so that more to present what we can do with a quantum computer, and on which domain it will be beneficial. And lastly, we plan also to have plenary conferences where we'll invite speakers to talk about challenges in quantum computing, and presenting what is quantum computing to a larger audience. Okay, and finally, I will finish this presentation with presentation of the quantum learning machine. So Olivier told us a few words about this already, but here in Romeo Computer Center, we have a learning machine, which is actually this one, the blue one on the bottom right, which is capable of simulating up to 30 qubits. And I think I'm not sure if I'm up to date, but the best machine is up to 41. Maybe Olivier can correct me. But also with these machines, we have a programming environment with MyQLM. I think that's also changed with the new Captiva framework, maybe, and providing a couple of services and some facilities to translate to different languages. So I'm done with my presentation, so I'll bring back, I don't know, yeah, Mark.
Yes. Yes, so thank you, Frederick, for this presentation. So everyone, for the moment, I don't have any comments on the chat, so we can move on the last presentation by Anna.
Hello, good morning again. So let me just pull up the slides. Okay, if you could just let me know if you see them okay.
Yes.
The slides, yes?
Yes, we can see them.
Okay, so thank you very much for the opportunity to tell you a bit more about what are the current activities in terms of quantum, let's say, at the University of Strasbourg, and more in particular at the new European Center for Quantum Sciences. So I am Anna, and I am working at the center as managing director for the quantum computing platform Access, and I will tell you a bit more about this later on. So a quick overview of the University of Strasbourg. You may know this already, but it's one of the largest universities in France in terms of number of students, but also in terms of research activities. It is very international, so 20% of the students at the graduate level are, let's say, undergraduate and graduate level are international, and 50% of doctoral candidates are also international. You see here some key figures: the number of PhD awards and PhDs and masters awarded each year, and as well a large number, over 3,300 research and teaching staff. The university covers all fields of sciences and humanities, and it's about 70 research units. Some figures that are given, let's say, independently by a ranking by the journal Nature. It's a little bit old now, 2017, but it hasn't been repeated since. Is that it's University of Strasbourg is the first university in Europe in terms of its impact on innovation, before some very famous universities as Harvard, Yale, and so on. Of course, if you're interested in this kind of metrics, there is the reference to this Nature ranking, and 16th in the world. So how this translates, let's say, into direct economic impacts is that for each €1 invested in the university, about €4 go back to the local economy as benefits. So a couple of words about CESC, our institute. This is a new institute created and let's say opened last year, not yet officially inaugurated. This will the official inauguration will take place in October this year. And it's located in the campus of Kronenburg, so the CNRS campus of Kronenburg. We are part of, administratively, we belong to the ISIS Institute, which is Institut pour les Sciences Ingénierie Supramoléculaire, which is located at Esplanade. So the center is really international in terms of staff, but also in terms of activities. And it's multidisciplinary in the sense that it covers different areas of science and applications, physics, chemistry, materials, photonics, computer sciences. Not all, let's say, activities that are affiliated to CESC are actually hosted at the center itself because of this affiliation with ISIS. However, so we are a little bit delocalized, but let's say the main activities are here. We are covering basic and applied research, as I will tell you a little bit more about afterwards. And what we are particularly proud of are the different types of partnerships that we have been able to establish over the years. So both at the local level, also in terms of regional activities, but also nationally and at the level of Europe. So the center has been supported, its creation has been supported by the University of Strasbourg and the CNRS, the Region Grand Est and the Eurométropole de Strasbourg. What we are trying to develop within the center is, let's say, activities that are really interdisciplinary and intersectorial. This means we are aiming at really fostering collaborations with industry and in particular technology transfer activities that could benefit companies. One successful example is the recently launched startup QPerfect, which is developing tools for simulation for quantum computing. They are also located here at the center. And we are currently expanding with a new building that will be attached to the current one, which is now being constructed and will open next year. So this will allow some additional lab and office space. In terms of activities and research areas, there are several and really go from fundamental research, light matter interactions, quantum theory, to more, let's say, advanced or applied topics that would include quantum computing. This is what I will focus on today. Engineered quantum systems, study of different types of quantum matter, molecular systems and others, and advanced numerical methods that support these different fields. So currently, as mentioned, we are a bit more than 40 staff, but this should double in the next years, and it's actually growing quite fast, in particular when we will be able to host the new labs and the new offices in the building next year. So I will tell you now a bit more on this project Access, which is a project that has started here at the center at the end of 2021. It's a for those who may know, it's a project supported by the EQIPEX program of the French National Research Agency, ANR, so Programme et Équipement Prioritaire de Recherche. It is part of the French National Strategy for Quantum because it's actually a part, it has been funded through this program PEPR Quantique, which is now ongoing, and it's gathering research project and another EQIPEX project that will also include additional projects that will result from the calls that are now open. So it's really, we are strongly embedded in the French national ecosystem through this project, but also more broadly via participation to European projects, namely the European infrastructure on computing with Rydberg atoms, Eureka. This is part of the Quantum Flagship Initiative you may have heard of, and numerous other activities that researchers here are involved in, namely in the field of education. So I will not go into details about that, but of course can give you more information. I think I have a relatively easy task now and will quickly go through the different slides that are more related to the scientific and technological aspect. I am not so much expert in this domain, but basically the quantum computation is allowing us, will allow us to address new challenges that are currently not addressable by classical computers or even high-performance computers. And this is the context in which the Access platform is operating. So with respect to the different systems that have been mentioned by Olivier and other speakers, I will just highlight some specificities of the technologies that we are using here. So, of course, there are different platforms that are currently explored for quantum computing, such as superconducting circuits, trapped ions, silicon quantum dots, many others, photonic qubits as well, as mentioned by Christophe. What we are working with here at the center are atomic qubits, so basically atoms that are trapped and manipulated individually to be able to store and process information. So again, we are say focusing on one specific technology. These are atom qubits. There are others being explored, let's say, through collaborations that we have with and partnerships we have with other research institutes. But this is, let's say, the underlying technology for the Access platform. Again, for technical questions, I would probably relate you to Professor Whitlock, who is the scientific coordinator of Access. I'm not sure if he's still on the call, but the idea here is to use quite sophisticated optical trapping, so lasers basically, that are let's say controlling individual atoms with specific patterns that are designed to perform this computation. In terms of mission for the Access project, it's the main objective is to build a quantum computing platform, meaning a quantum computer. So yes, there will be a quantum computer at the campus at the University of Strasbourg, let's say within the next years. We are now basically acquiring the equipment that is needed to assemble the platform. The system will be based on dual species, so it means two types of atoms, potassium and ytterbium, and it will the current plans are to have a platform of around 400 qubits based on this dual species. What you see on the right is a kind of picture of how the system will look like. So it is relatively compact in the sense that it will fit in a lab space of around 50 square meters. So what you see is an enclosure that will host the quantum processor and some of the vacuum systems that are needed for the operations of the processor. There is also some electronics and lasers around it, but basically everything fits in a room, in a relatively small room here in the lab. Now, Access is a tool that is supposed to be open for research and education, which is, again, another specificity of the project. So it's not, let's say, to be exploited commercially. It will be open for users in academia and industry to explore and develop use cases in different fields: chemistry, physics, mathematics, informatics, and beyond. So I will tell you a bit in the next slides how we are planning to do that. An important element is that it's not, say, a platform that should be isolated. On the contrary, it's, as mentioned before, embedded in the French and European ecosystems, and namely the integration with at the national level will happen through the integration with the high performance computing platform via the Hybrid Quantum Computing Initiative, which is headed by GenC. Just a couple of words more about the technology. Again, if there are specific questions, Shannon will probably answer them much better than me. What is an advantage of this platform is that is scalable. So it means that it can be, the number of qubits can be increased. and that currently there are some very promising results that are confirming that we can operate with the highly optimized gates that have been developed here also at the center by Professor Guido Pupillo. Very quickly, the applications and use cases are various, as mentioned by previous speakers, and we would like to explore as many of them as possible in different areas, both of science, but also in terms of applications. So we are really open to develop new partnerships and collaborations with companies in these different areas who are interested in either exploring further or beginning their journey towards quantum the usage of quantum computing. So please don't hesitate to get in touch to discuss this more. We already have a core group of experts within the Access project that are from different research areas. So I will not go into details here, but basically the different institutes of the University of Strasbourg and outside involved in the project cover chemistry, physics, informatics, material science, and mathematics, did I mention? So these are the different logos you see here. So it's really able to have, through the Access project, access also, or to get in touch with these different experts who are developing their activities in quantum. I think my time is running out, so I would just like to invite you to take a look at this website that you see here, Q4Chem. We are organizing a training event here in Strasbourg, 24th, 27th of October. It will be in person and also online, specifically for industries, but also students that are interested in either starting or getting an introduction about quantum computing for chemistry applications. The training will have 2 modules. The first 2 days will be quite general introduction to the topic, and also several companies, experts from companies that are currently working on quantum computing applications in chemistry, Repsol, BASF, BMW, and Roche. So you will get the chance to hear from them directly on concrete use cases they are thinking on. And the following 2 days, so Thursday and Friday, will be really hands-on exercises and coding workshops. So very much practical, that will allow participants to really acquire new skills and practical skills in quantum computing. So I think I will stop here, and if you have more if you would like to have more information, this is our website, and you can of course contact me, or I'm here for questions. Thank you.
So thank you, Hannah, for your presentation. So I will close this webinar. I will just share again my screen. Okay. So for closing this webinar, we'll talk about the Quantum Hub project at the region level. So currently we are trying to make a Quantum Hub project, so Maison du Quantique in French, in our region of Grand Est. So it's an answer of a call of project from the GenC. So this Quantum Hub project aims are targeting 3 different aspects. So the first one's about training and acculturation with training development, and also a part about attracting talents from international aspect. So the second one's about dissemination, so organization of information webinars such as this one, and also creation of a meeting place in Strasbourg for the moment, using the building of the CESC, for example, as Hannah told us just before. And the last part will be research and integration about the acceleration of the research part and development of use cases. So this project is under construction, and we need for feedback from companies, and also to have to be able to integrate them into this project, to be able to use quantum technology as our speakers present today in these different processes, and to be able to leverage this kind of technology to have acceleration or also to discover new use cases. So to conclude, I just want to thank you, all the 5 speakers, sorry for the teams, and also to thank our attendees. So for the moment, I don't have any question in the chat. So if you have any questions, the following, you can send me an email and I will push the question to our speakers, or you can also reach directly our speakers. So thank you all for your attention, and if you have any question, I'm here to answer it. So thank you.